Hello, everybody joining us. I see it's 1 minute past the hour, so I think we will get started. My name is Jon Sinnreich with GRL Engineers, and it's my pleasure as the chair of the Seismic and Lateral Loads Committee of DFI to welcome you to our second installment of our What's Shaking webinar. Today, we have a couple of fantastic presentations for you, very interesting from both speakers. Just a quick bit of information during the webinar, all attendees will be muted. There will be an opportunity for question and answer following the second of the two presentations. If you have a question, please type it into the Q&A question box, and we will try to get all questions answered at the end of the presentations. If for some reason we can't do that, if we run out of time, I will put you in touch with the speakers and you can have your question resolved directly with them via email. So without further ado, it's my pleasure to present to you our two speakers. The first one is going to be Professor Yazen Khasawneh and Spencer Ness of the University of Notre Dame. They will be presenting assessment of the liquefaction potential of wind turbine foundations using dynamic, nonlinear numerical methods. Gentlemen, please take it away.
All right, thanks, John. Sorry, the unmute button was not working for me. Sorry about that. So good afternoon, everybody. It's my pleasure today to talk about, with Spencer, about the assessment of liquefaction potential of wind turbine foundations using dynamic nonlinear numerical methods. This work has been supported by the Department of Civil Engineering and Environmental Engineering and Earth Sciences of the University of Notre Dame, and great help and support from Turbine. Today, our outline, we will have an introduction, then types of onshore wind turbine foundations, typical design approaches. They will talk about the specific model for the liquefaction study, how the ground motion were developed and selected, and discussion of outputs. Introduction. So based on the Department of Energy and the predictions of the generation of power in the US, we can see this from 2010 to 2022, and the prediction was for 2023. The gray line, the gray is the total million gigawatts that's going to be generated. And the green here is where we see the wind. So we can see the wind is actually did grow from 10% to about 22% by 2022 and 24% by 2023. The graph on the right-hand side, it also shows how are the renewable are taking more share, renewable in general, are taking more share of the generation of energy. And then the one next to it, it shows by type of those renewables, where the trend is going. And we can see that the solar and the wind are actually taking off as their contributors. And for us to maintain this trend in the wind, we need to make sure that the foundation systems are stable and are designed economically. Just for to know that one wind turbine foundation will cost about $1 million onshore, and we are talking about 25% of that, maybe even 30% is the cost of the foundation. So that is a significant contribution. If we can lower that, there'll be a lot of we can keep the trend of the wind going up. So that's in terms of the share of the wind, but in terms of the wind generation and how the technology developed over years. We can see back in the 1990s, we talk about 0.2 megawatt with with towers in the order of 8 some feet, then the 173 feet. Now we are here, but you can see we have the offshore, but now we are here in the onshore. We have about 150-meter wind turbine, and we are at about 6 megawatt production with the technology. Of course, we all know that the larger the rotors and the larger the blades, that's been more dynamic load, more demand on the foundation systems themselves. So we have to find ways that we can still put those towers in, and with the larger demands, and keep the foundation cost to acceptable cost, so we can keep the trend of the solar growth. Here, this is based on land only, market-based report for the share, and we can see this is for wind turbines, onshore wind turbine. The rotor diameters are increasing, and also the hub height is increasing. This is what's going to cause the additional load demands. We're going to talk about types of onshore wind turbine foundation. The first type that most of us are familiar with, and we see it because it's above the ground actually, it's the gravity foundation. The gravity foundation historically have been popular and still commonly used. They are becoming less efficient and costly as turbine size increases, because in order to come the overturning moment from the wind turbine, load to the wind turbine, those has to be huge. And of course, in addition to the reinforcement detail, the concrete footprint, the CO2 footprint, also due to the pouring those will be large. And I mean, really, we don't know how much we can get those larger to take the new demands. The other extreme is the deep foundations. Deep foundations, they've been used also on challenging sites. Deep foundation solution may be utilized. We all know that as we go deeper, the risk goes higher and the cost goes higher, right? So it's always, we want to go from to a deep foundation. We are countering more risk and higher cost. Monopiles are more common on offshore support offshore wind turbine. Intermediate foundations, they are foundation elements. There are several of those examples. The one I'm showing here, they are actually designed by patented and designed by Turcan. They are more complex designs, better leverage of structural components and strength of adjacent soil body. Require more exacting understanding of soil body and the use of advanced modeling. And that this is the focus of our present work. The intermediate foundations, they cut the cost compared to deep foundations, and also they can provide the resistance that's required for the larger demands. When those foundation elements, for example, we use a lot of pre-stressed components in the concrete that help also with the amount of reinforcement steel that need to be there. Now, the typical design approaches, I'm going to leave that to Spencer so he can take us through this.
Thanks, Yazen. Excuse me. So just to give everybody a little bit of background of how these foundations are typically designed, if you're not familiar with this process, is that the turbine manufacturer, the OEM, typically GE, Vestas, there's only a handful of them out there. They're really focused on how the turbine performs, how the tower performs, and then this is often the case with big structures. The foundation systems get devolved down to effectively just a spring constant. And so that's sort of the approach that has historically been taken and is typically taken. So the turbine OEM will develop a whole series of load cases through their analyses. Those will be then provided down to the foundation designer. The foundation designer is going to determine controlling cases and create a preliminary foundation design that can support those cases, both the structure and the soil and the ground around the foundation. But importantly, because we need to make sure, particularly that our rotational stiffnesses of the turbine are sufficient, we really need to take this into a finite element model regardless of condition to make sure that we're providing that stiffness, those spring stiffnesses that the turbine manufacturer is expecting. So this is sort of the typical design process. We take our design, we move through the finite element process in a static analysis, and we come up with these stiffnesses. We make sure they meet the turbine's manufacturer's requirements, and then we move forward from there. But those stiffnesses are really driven by the dynamics of the structure. So effectively, we're talking about a very large, very complex machine foundation. So dynamics are quite important to consider. And this is typical, again, since we're just moving everything to a sort of a static linear spring analysis, these dynamics are typically not considered directly in our analysis process or design process. So every time the turbine spins, right, we can think of any machine foundation. We have a certain frequency that it's going to operate within. Oftentimes in turbines, we're looking at somewhere between 10 and 20 RPM, maybe a little bit lower than 10, but all depends on the size and manufacturer. We call that the 1P frequency. So that creates a range of frequencies that we really want to make sure our entire structure, the foundation, tower, and turbine all combined, don't have a natural frequency within. We can also think that every time this turbine rotates, when that blade is in front of the tower, the cross-sectional area that the wind is blowing against drops, because we now have the blade shadowing in front of the tower. So 3 times our operating frequency, we've got this 3P range. So that leaves us with a complicated system to design within. So it'd be very challenging to get our entire structure outside of that 3P frequency. You can imagine this is effectively a single degree of freedom system. I can make my foundation only so stiff. Realistically, eventually I got to start stiffening the tower, which drives up the costs quite a bit. On the other end, if I try to make the natural frequency of my combined system on the low end, I get way too much motion, and it would cause lots of problems with the mechanical systems. So we're stuck trying to design the natural frequency of our whole system in between this 1P and 3P frequency. And then oftentimes insurers and finance people want to have a little bit of buffer on either side of that, narrowing the window that we're designing to even further. So that's sort of the challenge of the dynamic system. At the bottom of the screen, just to kind of highlight this is a time history of an accelerometer in the hub at the top of a turbine. While it's in motion, while it's in production, and you can imagine there's quite a bit of acceleration and different systems going on, both these 1P and 3P frequencies, and then certainly also the gearbox and other mechanical components that are operating there that are at a higher frequency that we're maybe not as concerned about when we're talking about the entire structure. So this brings us to kind of the focus of today's seismic design and liquefaction. Seismic design is certainly considered as the OEM goes through their load generation process, but oftentimes that gets then pushed on the foundation designer to make sure that the foundation is sufficient for seismic events. And this becomes a particular concern if you're in a site where there's a real concern about liquefaction. So as we continue to try to drive the growth of wind energy, more and more, we'll say marginal sites or sites that maybe were passed over previously, people are going back to and saying, hey, there's a real opportunity to develop wind here, but the ground conditions are not quite what we would have liked historically. And that's where the use of these intermediate foundations and more advanced foundations can become useful. Complicating this issue is that like I mentioned, there's often accelerometers up in the hub, up at the top of the turbine. If those accelerations exceed certain thresholds, those will initiate an emergency stop condition and basically put a brake on the turbine and shut everything down because there's too much motion going on, and there's a concern about the turbines, whether it's a resonant condition or an external environmental force on the structure causing damage to the system. So when we trip that emergency stop condition, we're applying the brake. If I'm in a seismic event and I'm now applying that brake, creating a big overturning moment to the structure, and having a seismic event where there's liquefaction that could occur. We have this combination of an extreme load with a reduced capacity that is really what we're interested in. Just to call out here, this image is not necessarily, or I don't believe is of a turbine during a seismic event. I believe it's just an undersized foundation. But you can kind of imagine, right, if we lost support of the ground from a liquefaction event, we could certainly see some sort of toppling like this as we lose support, particularly for these gravity foundations. So we'll talk a little bit about the model that we set up and how we did our calculation. So our analysis was done within Plaxis 3D, but we were looking at this intermediate type foundation, the Terracon, one of Terracon's designs. It's a circular cap, 36 foot in diameter, 6 feet thick of reinforced concrete. And then our turbine would basically be, the anchor bolts for the turbine would be here towards the center of the foundation. These are then supported on a series of ground anchors and 2 concentric rings around the edge of that cap. Importantly, in this foundation, and one of the complications that we had were that these ground anchors, some of them provide direct support to the cap, acting effectively as piles. Some of them are acting as tie downs, which creates a unique mechanism that we've been working to model in this effort. And I think we've come up with some better ways to approach that since we've actually completed this effort that we'd like to maybe iterate on this process and see what impacts that might have. We then get into the ground stratigraphy. So this particular stratigraphy is based on a site where one of these foundations were proposed at, where there was a liquefaction concern. The ground profile consisted of a series of layers of sand where there was liquefaction potential. So these K values are effectively the bulk modulus, or stand-in for the bulk modulus within the UBC sand model, which we'll mention. So effectively, as these numbers get larger, are expected the stiffness and strength parameters or I guess the stiffness parameters of the soil increased, and as well as certainly with the deeper layers, our liquefaction concern was less. These top 2 layers of soil were our primary concern. So we utilize the UBC sand model as implemented within Plaxis 3D to do this modeling behavior. For those who are maybe not as familiar with this particular constitutive model, we are able to capture a whole series of things: densification of the material, how that densification increases the stiffness behavior of the material, and then eventually the yielding and stiffness degradation. So that's basically what this top diagram is showing. Is this is taken from the development documentation around the UBC sand model. But as we cycle these loads and change some of the effective vertical stresses that we're seeing, things are behaving as we would expect. Similarly with excess pore water pressure buildup and those parameters as well. Getting into the model domain, we ended up having to create a relatively large soil domain as we were getting all sorts of fun impacts from boundary conditions during our dynamic analysis. So we ended up with a 400 foot by 400 foot soil domain in the lateral directions, and we went down to 150 feet. In the vertical direction, in our dynamic analysis, we needed to make sure that we were using non-reflective boundaries as implemented within Plaxis. So we used these free field implementation to make sure we weren't getting reflections back into our model. So moving quickly here through our load application. So originally, we go through a series of intermediate stages of installing the foundation, installing these ground anchors. As I mentioned, some of them are serving as tie down, some of them are serving as support to the cap. So we need to make sure that those are being installed and designed and the loads applied correctly. We then applied the self weight of the turbine and the tower at the top of the foundation level. We didn't directly model the turbine itself in it, just given the computational effort that we were already going through. So we simulated the weight of the turbine just as a surface load. And then we moved into applying that emergency stop load, that overturning moment that gets applied as we apply the brake up at the turbine. And then finally, once we have all those loads applied through static analyses, we move into our dynamic analysis of adding that that seismic motion at the base of the soil domain. So we then needed to find a ground motion that we felt was appropriate for this particular site that was being investigated, but that would also initiate a liquefying event. So we went through the process of selecting an ASC7 design spectrum, found ground motions in the peer database that were both regionally appropriate and matched our design spectrum. We then took those motions, did an additional step of spectral matching to really get ourselves dialed in to make sure we were initiating a liquefying event. And then we wanted to also match not just the frequency content of the motion of interested, but also the PGA. So we then scaled up that spectrally matched motion so that the PGA of that matched motion matched our original design spectrum PGA. So with all that, we applied all that to the strong direction to kind of simplify things and not have to repeat this process and have conflicting things going on in the weak direction. We basically just linearly scaled the weak direction motion based on the ratio of the strong direction motion at that time step to the original strong direction motion at that time step, and went that way to develop our time history. So you can see here our original time histories on the left. We focused in on the S wave arrival and that stronger motion duration. We took this about 45 seconds of motion, did our spectral matching, did our scaling of the PGA to create sort of effectively a synthetic motion that we were then going to apply to the system. And then again, repeating this process in the weak direction. The east-west was our strong direction, and north-south was our weak direction. So we'll then get into some outputs here. Let's see if this plays. So each one of these purple dots represents liquefaction and a stretch point within the model. Hopefully this is coming through reasonably well, but we get a lot of liquefaction in this upper layer. As the time history goes on, we get some liquefaction in the lower layers that we were concerned about, and then this repeats here. We are getting an increased sort of density of liquefaction points around the foundation. Some of that is just driven by the mesh sizing is much smaller to capture behavior around the foundation, but also that the foundation itself does, as it moves, does impact the liquefaction processes. Too far. So this is the same information as we saw in the animation, but just a little bit easier to look at. This is a section cut across the center line of the foundation. And so you can see liquefaction develops relatively quickly in that upper layer. As we get into the strong direction, the strongest portion of the motion, we're also getting some liquefaction in the secondary layer. But importantly, with this foundation, again, the way it's designed with these tie-down points, we are seeing some densification of this upper layer, which is why we believe we're not getting as many liquefaction points directly above directly below the cap as that increase of an effective stress from those tie downs pulling down on the upper foundation are impacting the effective stress development. And that's an important part of how this particular foundation works. And it's also great to see that the constitutive model is capturing that as well. So importantly, we wanted to look at how the foundation actually behaved during this motion. So this is a series of time histories measuring vertical displacement along the center line of the foundation. So I've got this blue line, which is basically on the lower side, the side that the foundation is overturning towards. This gold line is on sort of the upward side of the foundation and then along the center. So we're getting this motion. And importantly, we're kind of getting some differential displacement, which then somewhat levels out as the foundation sinks within the soil, and we're getting some additional support as the entire system changes and the loads resolve through the system. So running a little bit behind here, but just wanted to go through some of the quick takeaways that we had from this work. So that we found that the UBC sand model worked well in this dynamic analysis within Plaxis, capturing the behavior that we expected, and it made sense. We think that this analysis process could certainly be utilized to assess other designs, modifying different parameters of the soil to reflect interventions and remediation that might be done to impact liquefaction potential. Additionally, this synthetic ground motion assembly was pretty successful in capturing a motion that, while is probably scaled up quite a bit from what a true design event would be, it did generate the liquefaction event that we were looking at. Some of the challenges we were running into is that, as I mentioned, we have, particularly with these intermediate type foundations, lots of challenging structural elements that challenge the modeling effort, where you really need to understand how is the structure designed, how is the structure supposed to perform, particularly at these connections between these ground anchors and the upper cap, all sorts of fun things that went on there to try to make sure we're capturing it, and some of the things that we're continuing to look at. And this was also quite a large computational effort, just to even model these 45 seconds of dynamic analysis. Took many, many days to do a single run of this. So in that effort, we have been continuing some work on this, looking at leveraging high performance computing resources, both here at the university and with NERI and NSF, to really understand this. We're looking at maybe moving away from Plaxis and repeating this process in other software packages such as LS-DYNA, to be able to leverage some of that additional performance from the high performance computing. We've also wanted to look at the same process with a similar gravity or just typical deep foundation design to sort of compare and contrast how much do these intermediate foundations, do they perform better than some of the more typical foundation designs? And we certainly want to sort of iterate this given the sensitivity, of course, of liquefaction to the ground profile. So a few minutes over here, but hopefully Ben won't hold that against me too much, but I'll hand it back to John, I think, for the second presentation.
Yeah, thank you, Spencer and Yazen, for a very informative presentation. Our second presentation for this webinar comes from Dr. Ben Turner of Dan Brown and Associates on the topic of seismic design of structurally reinforced slopes.
All right. Thanks, John. And thank you, Spencer and Yazen, for that presentation. And thanks everyone who's tuned in today. Appreciate your time. So the title of my presentation is pretty broad, but really I'm going to be speaking about something very specific today, which is how do we include structural resistance from a pile element, for example, is what I'll mostly be talking about, but this could be extended to other structural systems like walls, embedded walls, or anchors in pseudostatic limit equilibrium method slope stability analyses. And even though that's a mouthful to say all that, that is, of course, really like the simplest way that we can do slope stability analysis for a seismic case. And I won't be speaking today about more advanced modeling approaches like what we just heard about from Spencer, using continuum numerical modeling, even though in some cases that might be warranted or appropriate to study the type of behavior you're interested in with your system. Today, I'm talking about a simpler approach, which is always good to have in your pocket, even as just a first step if you are doing the more advanced modeling effort. So I'm going to start by talking about some of these concepts, just the fundamentals of them in a non-seismic case, really, and then we'll build upon that. And mostly what I'll do today is try to highlight some of the differences between our approach to this problem for seismic cases versus non-seismic. So to that end, I want to make a quick plug here. There's a report published by DFI, I think earlier this year, called Guidance for Factoring Deep Foundation Structural Resistance for Landslide Stabilization and Excavation Support. And there's you can find it on the DFI website, or if you're You can take a screenshot of that web address right there. You can grab it right now. It's free, and it talks about what I'll be speaking about at the beginning here today for non-seismic cases, addressing the fundamental mechanisms at play here and how to identify the appropriate amount of resistance for limit equilibrium slope stability analysis. So let's start with the real basics here. On the left, we have an illustration of a slide mass, and it's been stabilized by a deep foundation element. I'll just say pile generically, passing through the slide mass and then embedded in the stable material below. And as a result of the slope movement, we get an earth pressure distribution acting above and below the slide plane. So above the slide plane, it's really a driving force pushing down slope. Below the slide plane, it's a resisting mobilization. And we see that the pile in this case is deforming primarily in flexure in response to that slope movement. If we represent that as a free body diagram, which is really the backbone of the so-called method of slices or limit equilibrium slope stability analysis, we have the internal body force, that's the self-weight of the slide mass, which can be resolved into parallel and perpendicular components along the base of the slice, where we have a normal force that provides confinement, and then a shear force or stress, which is the resistance of the geomaterial, the soil or rock there. Our pile passing through the slide mass also gets cut at the slide plane. And so it's evident from this diagram that the internal shear force in the pile, the mobilized shear force, is the pile's contribution to resistance against sliding of this free body. There would also be a moment there where we make this cut, although I'm not focusing on that today. That's also a part of the statics of this problem. So the mobilized shear force at the depth of sliding is the correct resisting force to be considered in this type of analysis. The basic premise of limit equilibrium slope stability analysis is that every component of the system is at a limit state. And some of this might seem kind of obvious, especially if you've heard me speak about this topic before for non-seismic cases, but I'm re-emphasizing some of these fundamentals because some of these things break down or change a little bit when we're doing the seismic case. So bear with me here for a few more minutes. So what I generally say, and for non-seismic cases is true, is that for consistency with the basic premise of limit equilibrium slope stability analysis, everything in the system should be at a limit state. That, of course, includes the geomaterials, but it also includes the pile resistance. So for the geomaterials, that's easy. We don't even really think about it usually. We just say this soil has a friction angle of 34 degrees or an undrained strength of 4 KSF. And we as engineers recognize that it takes some deformation to get to that shear strength. If we think about a stress strain plot from a laboratory test on soil, it doesn't just go straight up to the shear strength. There's some curvature and strain to get to that point. We know that it's the same thing for a pile. It doesn't just suddenly fail in flexure or shear. It takes some displacement to get to that point. So the premise here is that you should be using a resisting force representing a limit state of the pile soil lateral interaction behavior. And multiple failure modes are possible. We'll show some sketches of those on the next slide. And we want to know which one of those failure modes controls. And what I mean by that is which one occurs at the lowest level of slope deformation, which corresponds to the lowest level of mobilized shear force. When that failure mechanism has occurred, we are at a limit state for the pile system. So here's sketches of the 4 potential failure modes, 2 geotechnical and 2 structural, that I've defined. And the real motivation for that DFI report and putting together this talk in the first place is that what we often see in practice is people use the structural shear strength of the pile element as the resisting force in the slope stability analysis. And that implies that the shear failure mechanism is the controlling mechanism that occurs and defines the limit state. And that's problematic because for a wide variety of conditions, that is unlikely to be true. What we often see is that flexural failure or flow around failure will occur first, meaning as the slope displacement gradually increases, you get a flexural failure first prior to shear failure, or one of the other mechanisms. I will point out that the pushover failure simply indicates there's inadequate embedment into the stable material below, like I'm showing here. That should never actually control the design, because the right thing to do there is just to make the pile longer. So you can kind of ignore that one. Okay, so let's dive into this a little bit more, and also get a snapshot of the analysis that is required to understand which type of failure mechanism controls. Okay, so you see here a series of plots that are the output from, in this case, LPile, although this could be done with any software, PY method software that allows simulation of relative displacement between the ground and the soil. So we have a series of 4 plots here: deflection, curvature, moment, and shear force. And in the plot on the left, you see this blue line near the top. That's actually the profile of ground displacement imposed relative to the pile foundation. So it's on the order of about a foot or 14 inches, and it's a constant value down to the depth of sliding of 20 feet, which comes from the slope stability analysis that's being done in concert with this laterally loaded pile analysis. I do want you to note that the pile in this case is also deflecting about as much as the ground, at least at the ground surface, at the point when a failure mechanism forms. In this case, that failure mechanism is flexural failure, or a moment failure. And we can see that because it's most notable in this curvature graph, where the curvature spikes to a really high value. That means that a plastic hinge has formed. And when we look at the moment graph, the peak moment is near about 6,000 kips, which is equal to the moment resistance of the HB 14/117 steel pile that we're analyzing here. And when we look at the shear force plot, the shear force that we're interested in for the purposes of our slope stability analysis would be the mobilized shear at the depth of sliding. So at 20 feet, it's on the order of 50 kips. And it's notable that the shear capacity of this pile is more like 500 kips. So when the plastic hinge forms, when a flexural failure occurs, which is the controlling mechanism, our mobilized shear is only on the order of about 10% of the shear capacity of the pile. So you would be wrong by a factor of about 10 if you input that full structural shear strength into a limit equilibrium slope stability analysis. In other words, it's impossible to ever mobilize that much shear force, because a flexural failure would occur first, the pile would simply bend over, and the slope would keep moving. So one of the reasons why shear failure is unlikely to occur in a wide variety of conditions is that the moment demand is increasing as the slide plane gets deeper, as a function of 2 terms being multiplied by each other. It's essentially the resultant of this earth pressure distribution times the moment arm from its centroid down to the point of maximum moment below the slide plane. And so it's 2 terms multiplied by each other. It's increasing exponentially as the slide plane gets deeper. Whereas the shear force is essentially increasing linearly. It's just the resultant of the earth pressure distribution. So you can almost see that in these 2 plots when you compare them to each other. And for that reason, your moment is always running up higher than your shear force. Okay. We did a poll during a DFI S3 event about 3 years ago, where we asked people how they did this prior to seeing this presentation, and more than half of them indicated that they are using the structural shear strength of the pile material in slope stability analysis. So there's definitely a gap between what's being done in industry and I think what's more appropriate to capture the mechanics of what's going on here. Okay, so to summarize, for kind of the general case before we jump into seismic, shear failure is unlikely to occur prior to one of these other failure mechanisms, particularly a flexural failure if it is going to be structurally controlled, or a flow around failure where the ground just keeps going and the pile has not failed. And therefore, it's usually wrong to upfront just assign the structural shear strength as the resisting force in a slope stability analysis. So crucially, this third bullet point, which also applies for the seismic case, is that you have to do a separate laterally loaded pile analysis in order to determine which mechanism controls, and by extension to determine the correct resistance, meaning how much shear force is mobilized when one of these other failure mechanisms occurs. And that does not appear to be the industry standard quite yet. Okay, so let's get into the seismic case. What is different about this? So for the non-seismic cases, or kind of generically what I was just talking about, we're usually talking about designing to a target factor of safety on the order of 1.3 or more, somewhere in the range of 1.3 to 1.5 typically. In the context of LRFD, we would call this a strength limit state. For allowable stress design, like for the building code, this would just be the slope stability case, and that's the target factor of safety. And we ignore the deformation in that sort of analysis or reporting of the results. What I mean by that is when you analyze a slope and say the factor of safety is 1.4, we don't also say, and the displacement that goes along with that is 2 inches or whatever, for a couple reasons. One, we don't directly consider it in our analysis, particularly for the geomaterials. Like I said before, we just assign the shear strength without direct consideration of how much displacement it takes to get to that. But also because we're talking about what I've said here, a fictitious condition, which means because the resisting forces are larger than the driving forces, by definition, if our factor of safety is in this range, then we have satisfied the conditions of equilibrium. There shouldn't be any significant displacement in our slope. So the displacement is essentially not meaningful and not really of interest, and should be minimal or negligible in our slope anyway. For the seismic case, things start to change in that regard for a couple reasons. And when we're doing seismic slope stability analysis, we're likely trying to satisfy one of 2 possible sort of criteria for acceptance, depending on the code or the design criteria of our project. The first is that the code document might define a target pseudostatic factor of safety. In that case, it's usually on the order of 1.0 up to maybe 1.1. So it's low in that it's close to 1.0. It's close to a condition of equilibrium, meaning that there might be some movement of the slope. The second one is that particularly for performance-based design criteria, sometimes the factor of safety is not even a consideration, and instead we're just designing to a maximum permissible slope deformation, usually on the order of a couple inches or say 10, 15 centimeters kind of thing. In either case, there's potential for large deformation. It's particularly when we're talking about seismically driven slope instability. If we have a seismically induced strength loss like liquefaction and a lateral spreading type mechanism, or a flow failure or cyclic softening, we might see very large displacement when we have mobilized the resistances that we're looking for from either our geomaterials or structural. And also the displacement itself has maybe become the performance metric of interest. So we can no longer say that deformation is not important. I previously said that the pile resistance, the mobilized pile resistance used in your slope stability analysis, should correspond to a limit state. And we should recognize that this may require significant displacement to develop. So even in the case of the example I showed several slides ago, where the ground moved about a foot, maybe 14, 15 inches to form the flexural limit state, the pile was also moving that much. And that pile supported a bridge abutment in that case for that actual project. And in any case where we're talking about these structural elements actually supporting a structure, that magnitude of displacement is probably unacceptable. We don't actually care how much the ground displaces, but we care about how much our structure moves, right? And so we can no longer ignore the displacement of the structure. And we are likely talking about a level of displacement corresponding to the limit state that exceeds what we can tolerate, okay? So let me kind of just put some numbers to this for an example. We might be designing a bridge, and on the approaches, the banks are predicted to undergo several feet of displacement along a liquefied layer prior to the pile reaching a limit state. Let's say it's flexural failure, by far the most common, due to the maximum moment at some point below the depth of sliding. Well, if the pile above there is going to move 3 feet, clearly that would be unacceptable. And this is the key point. That means that the amount of structural resistance that we can rely on back in our slope stability analysis is now something less than what corresponds to a limit state. So we don't necessarily reach a limit state when defining the pile resistance that we can utilize in a pseudostatic seismic slope stability analysis. Okay, so how do we account for this? I'm going to focus on this first bullet point here. We're going to quantify that mobilized structural resistance in exactly the same framework that I just talked about, where in an L-pile type analysis, we displace the ground and we gradually increase that level of displacement until now, instead of trying to define when a failure mechanism occurs, we're looking for this so-called compatible displacement, and I'll define that here in a minute. Alternatively, we could use something like a ground improvement system that isn't flexible. It doesn't require significant displacement to mobilize. So you can imagine something like a block of soil cement mixing or a grid of CSM columns or panels is relatively stiff. And so as soon as the system starts to move, we can rely on its full shear strength. So that's an alternative that could be viable if we have unacceptable levels of displacement, to use ground improvement to stabilize a slope. Here's just a photo of the kind of displacement I'm talking about that would likely be unacceptable if our structure moved this much as well. So this is lateral spreading features on the bank of the Colorado River from the El Mayor Cucapa earthquake in Baja, California in 2010. The ground moved on the order of 3 to 6 feet. It actually moved even more on the other side of the river. So if the structure were to go along for the ride, that would be an unacceptable level of displacement, obviously. But what we're looking for is the so-called compatible displacement, which hopefully is something less than the full free field displacement. And this is sometimes called the pile pinning method or the restrained displacement analysis. I tend to shy away from those terms because they characterize it as if though what we care about is reducing the ground displacement. I don't care if the ground itself moves 5 inches or 50 feet. What I care about is making sure that the structure doesn't move, to an unacceptable amount. So I prefer this term, the compatible displacement method. And what we're looking for is compatibility between these two mechanisms that are both a function of the ground displacement. The first is that as the ground displacement increases, we mobilize more pile resistance. We mobilize more internal shear force at the depth of sliding. And like I alluded to a minute ago, we're going to quantify that using the same procedure as before, but our compatible displacement likely occurs at a level of mobilized pile resistance less than that corresponding to full structural failure of or a failure mechanism in general of our pile soil system. The second mechanism is ground deformation as a function of pile resistance. So this is within the context of our slope stability analysis. With a given level of pile resistance, how much do we predict the slide will move? And to get that movement, we need to do something that goes beyond just the basic limit equilibrium slope stability analysis factor of safety. We're going to do pseudostatic factor of safety or pseudostatic analysis to compute a yield acceleration, which is by definition the horizontal seismic coefficient that corresponds to a factor of safety of 1.0, so at the point of equilibrium. And then we're going to estimate slope displacement as a function of that yield acceleration. We can either do that directly using Newmark sliding block analysis. So if we have ground motion records for our project, or we're willing to come up with them for this process, we can plug those in directly and essentially integrate versus that acceleration series. And whenever the acceleration exceeds the yield acceleration of the slope, we get some movement. So we keep track of that and we add up that movement. The cumulative amount of it is the slope displacement. Or we can do the simplified Newmark sliding block analysis, which means using a closed form equation, an empirical equation, where we plug in the yield acceleration and other parameters that describe our slope and its dynamic characteristics, and we spit out an estimate of the slope deformation. Those are based on large databases of seismically induced slope failures. So what that looks like in kind of this final configuration is a plot like this. So there's a lot going on in this plot. The compatible displacement is where these two curves that have opposite directions cross over each other. So in this case, it's this defined where they cross. This vertical dashed line takes us down to the displacement axis, and it's on the order of about 8 inches. Okay, so we're looking at two curves representing those two mechanisms that I just spoke of. The first one is the pile resistance as a function of increasing ground displacement. So just like you'd expect, when the ground displaces relative to the pile, we mobilize more and more resistance. You can see that this keeps going off the edge of this plot. Somewhere near here, the curve is kind of leveling off. So we're either approaching a flow around failure or structural failure of the pile would occur, probably a flexural failure. In fact, in this case, it would have been a flexural failure. The other series of curves, which are bounded by this shaded area, represent our estimate of the slope displacement as a function of pile resistance. And I have 3 different curves plotted on here, and that's an effort to capture the significant uncertainty in this type of analysis, which I'll speak to a little bit more in a second. But basically, these curves show the opposite trend. As you get increasing ground displacement, as the level of pile resistance increases, you see less slope displacement, just like you'd expect. So again, where these mechanisms cross or converge is defined as the compatible displacement. So there are a whole bunch of iterations of those two analyses that I spoke of previously, those two mechanisms, in order to define a curve like that, and then outspits the compatible displacement, which is the ground displacement. When we've plugged that into our laterally loaded pile analysis, that produces the final answer, so to speak, in terms of the pile demands and deformation. All that makes it sound pretty simple, save for the numerous data points in that plot, which each require their own analysis. But to wrap things up, I want to speak now to some of the many challenges that we actually face in this type of analysis. And really, even though the analysis itself is relatively simple, which is one of the good things about it, we're simulating a very complex problem here, and it's important for us to keep that in mind when we're doing this sort of thing. Okay, so the first one of those issues I've dubbed the limits of limit equilibrium method analysis. When we have a low angle slide plane, like we tend to see with these seismically induced slope failures, especially along a weak layer like a liquefied layer, the base of that slice is nearly horizontal, right? And so we've got a large seismic force, that's our driving horizontal force, which is the seismic coefficient multiplied by the weight of the slice. And then we've got a relatively low shear strength along the base, especially if we have a liquefied layer. So in simplified terms, our factor of safety, at least for one slice, is the ratio of that low shear strength to a large seismic force. We know by definition this number is going to be close to 1 because we're right around the point of equilibrium, dipping below it when things move, which means basically that the answer is sensitive to both of these parameters. It's sensitive to the magnitude of the shear strength and of the seismic force. And there is significant uncertainty with both of these parameters. And that's the rub with this whole thing. They both change with time, right? The seismic force directly changes as our acceleration changes during shaking. And the shear strength is changing with time, especially if we're talking about liquefaction. That doesn't just flip on like a switch. It develops during the earthquake record. And even once we're in a liquefied state, it's not necessarily constant. We can get dilation spikes where things stiffen up again and all these things. So we are drastically simplifying this into 2 numbers that we represent as constants, neither of which are really constant. How do we account for that? We can put parametric bounds on these and vary things when we do our analysis, which helps. But I think we also just need to do a reality check that what we're coming up with here is an approximate answer. We also have to scale things in the out of plane direction in order to make a link between our pile analysis, like an L pile, and then our slope stability analysis, which is 2D. So we have to take that pile resistance and represent it, per foot or per meter in the unit width out of plane direction. And there's not great guidance in this in the literature or in the design codes that talk about this. And so this is something I've come up with that's just based on geometry and soil properties to define an equivalent width of the zone of influence of this wedge of soil that an individual pile interacts with. This also gives you a way to know if your deep foundations are spaced close enough so that their zones of influence overlap. So this can be a helpful tool along the way of this analysis. And then finally, I want to mention that everything we've talked about so far is just looking at what's going on in the ground in terms of the interaction between the foundations and the moving ground. But there's interaction also between the superstructure above ground, whatever it is that these foundations are supporting, and the system response. So, and this illustrates like a bridge where we've got the ground surface is shown here below the shaded zone, so at a depth of 40 feet below the top of the column or pile. And the response above ground depends on the boundary conditions that I put in there. So if it's perfectly pinned but allowed to rotate, like in this black line, of course it can't deform at the top. Whereas if it's free, we get a lot of deformation at the top. So that would be just, whether it's restrained by a bearing at the top and pinned or allowed to translate freely. And we get a huge difference. This is when subjected to ground deformation. We get a huge difference in the moment profile, both in terms of the depth and the magnitude of the maximum moment, but also just the shape of these profiles in general. And so this just highlights the fact that the demands coming in from seismic ground deformation are not just a foundation problem. It also has implications for the portion of the structure above ground, including the column demands, but also the overall response and deformation of the structure. So I've just touched on, in the short time we've had today, 3 or 4 issues that come into play when doing this type of analysis. But to kind of tie this all back together, the key premise here is that the amount of resistance that a structural element can offer in the context of a limit equilibrium slope stability analysis for the seismic case is likely even less than what corresponds to the full flexural strength or shear strength of the pile element. The only way to find that out is to do a separate laterally loaded pile analysis. So that takes us to the Q&A segment here. And just to remind everyone, the questions, if you have any, you have to type them into the chat box and then we'll answer them.
Thank you.
Yeah.
Thank you,
Sorry,
Dr.
John,
Turner.
go ahead.
Yeah, I was going to say, we don't have any questions. It sounds like everybody covered their topics very well. Thank you all, gentlemen. Much appreciated. If you do have follow-up questions, there will be an email address to send those to. Yeah, go ahead and advance, please. Yeah, PDH certificates are available for paid registrants. And after completing a webinar evaluation, you can register at dfi.org for other webinars. We plan to continue this great series next year. Stay tuned for future dates. Please do give us your feedback and suggestions. We'd love to hear from you. Direct any questions or suggestions that you may have to the email address you see right there, techactivities@dfi.org. Thank you very much, everybody, for joining us today. It was great. I look forward to seeing you again.